Alright, so this is the beginning of the session. It's 10:03. Um, thus far, we've talked a little bit about enolates and how there could be two resonance structures, and both of them are valid when you draw the mechanism, and you get to pick which one you want to use. I just prefer to use this one because this is a major contributor because the anion is on the more electronegative atom, the oxygen. So how does this show up in a problem, in a mechanism problem? Well, the first thing is, let's discuss how I would get this product as fast as possible. We know that the attacker is at alpha carbon. Okay, we're going to make the point of attachment at that carbon. So I'm going to draw the same exact molecule, but I'm going to flip it. I reversed it. Also, I swung this methyl group downwards. Those two molecules are identical. Okay, they're just drawn in different angles. You want to imagine that you have a carbonyl group, another one of itself, and yeah, if you literally think that you're making this anion, then you can directly attack like this. Okay, so that's just part of the mechanism. But what I'm trying to impress upon you is that you're making a bond to the dot. From what carbon? From the alpha carbon. So we have alpha to the dot. That becomes an OH. Originally it was an O minus, but we're going to protonate it with water. Okay, and let me just double check if there's in the chat. And then what else? That dot that was attacked has an alpha group. Okay, that is your final product for the aldol. Okay. Now, for the mechanism, you want to go ahead and deprotonate. That's pretty simple. This is all in the videos. I just want to make sure that there's no confusion in terms of what I would accept as a proper answer. And we have OH minus. And we're using sodium hydroxide. So we're going to make the enolate. Okay. The way that I show it on my videos is that I'm not going to put the lone pair on the carbon. Instead, I'm going to swing it to make a double bond and make the oxygen anion. I don't know if I use equilibrium. I should. No, I probably didn't, actually. And then I have this. And this is the same. This is the same exact structure that I have up here. Okay, same exact structure. Now, in terms of the attack, okay, so how do I get the attack from the carbon when there's no anion at the carbon? There's no anion at the carbon. So let me show you how to do that. You have another one of itself, and you're gonna remake the double bond, attack this carbon. Okay, you start from the middle, and then you have that. Okay. Again, this is all in the video. Now the thing is, I didn't do the trick where I flipped the molecule. Sorry about that. I'm drawing exactly how the carbons are arranged, and I made the bond where I made this bond right here, right from the alpha carbon to what? To the dot. And then I have the O minus, and I have the rest of the chunk. So that molecule is almost identical to this, except I need to add one more hydrogen. Okay, so that's how you get the product using my resonance structure. But if you want an alternative, okay, if you don't like doing this, you're free to do it this way. It's just that I don't teach it this way. So it's going to be very rare that you're going to see me do a mechanism where I have a C anion. And how do I do that? Same first green arrow. Okay. But now my second arrow is going to push these electrons directly onto the carbon, like that. So I'm going to get a different structure as an intermediate. I'm going to get the enolate, but now the enolate in the form of the carbon anion. So what I'm doing is I'm comparing these two. But again, those two represent the same anion because they're resonance of each other, resonance contributors of each other. People like doing this way. I understand that. Why do people like doing this? Because now all you have to do is a direct attack. You don't have to worry about remaking the double bond. It's already there. Ultimately, if you follow those arrows, you get exactly the same thing. See, these two are identical right there. Okay. So whether you think you're attacking from the C anion, or whether you think you have an O anion and you eventually get that alpha carbon to attack, it doesn't matter to me. You can draw either mechanism. This is important because not only do we have aldol, we have aldol condensation. We have intramolecular aldol. We have Claisen. Claisen is still an enolate. So you can draw the Claisen attacker enolate in two different forms. Okay, what would be the difference? An ester, you would have an OR group on here, an OR group here. But you could still have the same type of resonance. So again, don't get hung up. If you like doing it this way, because you literally see the carbon anion, then go this way. But again, my preference is to draw the more contributing resonance structure. Okay. If there are no questions about that, let me just label this real quick. This is the aldol at the top. Why don't I show you that the last new reaction, and it's actually a sequence of reactions to finish out this unit. Okay. So unit 9, and this is reaction. Okay, give me a second. Let me find it. Okay, so the last, it was this one, right? So we had a Claisen at 9F. We had a cross Claisen at 9G. We'll go over some Claisens a little bit later. So we're up to H, 9H. Last reaction. And actually it's not a reaction, it's a set of reactions that you've seen before put together in a sequence. It has a name though. It's called the Aceto, Acetic, Ester synthesis. The name is very, very weird. Not because of this, I'll show you how we got that term. It's the idea that that's actually the starting material, right? Normally when you say synthesis, you think that this represents the final target. This represents actually the starting material. And the starting material is acetoacetic ester. I'm trying to figure out which acet is which part of the molecule. So let me draw it first, and maybe I'll jog my memory. Okay. Your ester could be ethyl, methyl, propyl. It doesn't matter. You're going to see that at the very end, we're going to lose it anyway. Acetic ester is that part right there. Okay. They have another aceto group to have this acyl group, or the ketone, with the methyl. So the methyl is important. The methyl is the aceto part. Aceto. Okay. Forget about that. I don't even know why I went down that road. But this is literally acetoacetic ester. Maybe that's why I did that. Okay. You start from there. The first reaction is a base. But look at the base that I'm using. NaOET. This is a concept where you want your base has to match your leaving group. In one of the videos I explained that. This harkens back to the Claisen, where we have an ester and we want to deprotonate the alpha carbon, but we don't want to have exchange. Or if we do have exchange, can you imagine what happens with exchange here? The O-ethyl will replace the O-ethyl. So there's no change, right? But sometimes the O-ethyl will rip off this hydrogen, and you get an anion. So that's what the first reaction is doing. The second reaction is an alkyl halide, typically. And let me give you something that we can track. We're going to track where this alkyl halide goes based on this double bond here. And you're going to attack this bromine. Not the bromine, you're going to attack this carbon. This is a 5-reaction synthesis, commonly known as the acetoacetic ester synthesis. The next one. What is going on here? NaOH, water, heat. We have an ester. This is hydrolysis, but it has a special name. Its name is saponification. Okay. Don't forget that. I think that was on your last exam. With saponification, you make the carboxylate, so you make the O- actually. So I am going to put a little bit of acid to protonate that O-, that carboxylate, to make it an OH. So visualize. At this point, you should have a carboxyl group after step 4. Think about the type of molecule you have if that was a carboxyl group. Think back to your unit. There were only a few reactions with carboxylic acids. One of them was Fischer, esterification, but we're not going to do that. We're going to heat it. What is that? Is that even a reagent? What can this do? This is your reaction where you bake edibles, marijuana. What happens in that process? You decarboxylate. So do we have a chance to decarboxylate here? Yeah, there's your beta keto. This is a weird sequence, because what did I just say going through these reactions? We're getting rid of the ethyl group because we're making a carboxylate. We're getting rid of the carboxyl group because we decarboxylate. We lose more than half of this molecule. Okay? But what else do? We gain. What do we gain? We gain these carbons right here. Okay? So, let me get us started. I'm curious, and this is going to be part of your assignment, or this is similar to your assignment at the end of class, is how do you process this information? I said a lot, okay? But how do students process this? How do you have recall when you see something like this? The recall that I have is I like to categorize the reactions. So for instance, I'm going to do it right here. After the first reaction, I deprotonated the alpha carbon. So literally 1, 2, 3 words. Deprotonated the alpha carbon. What is this? Okay. I'm imagining a minus charge right here. So I know that it seems a little bit contradictory. When I visualize a reaction happening, I actually do visualize the carbon anion. But when I draw the mechanism, I draw the oxygen anion. Okay. But I know I'm going to make a connection between this alpha carbon and this carbon here because this is electrophilic. Opposites attract. negative charge, partial positive. So we're doing a substitution. I mentioned this was saponification, but then we're going to protonate. So we're going to saponify and then protonate, but that ultimately will give me a carboxylic acid. This is saponification and protonation. And remember what the last reaction is? You go to heat this carboxylic acid that has a beta keto. This is decarboxylation. All right, hopefully you have those notes. We're going to draw the product of each of these reactions, and then ask ourselves, why would people ever do this? What is our final product after these 5 reaction steps? And how can we get the product faster without having to draw all the intermediates? Because ultimately, that's going to happen on the exam. I'm just going to give you a set of 5 reagents, and either on a scratch sheet of paper, you'll figure out, or in your head, you got to figure out what the final product is. It's hard to visualize the final product because, again, you are losing so many atoms in the process. But this is a popular synthesis, and we're going to see what we make in just a bit. We have this acetoacetic ester. Again, it could be O-ethyl, O-methyl, O-propyl, whatever. But just make sure your base matches. So the base is going to be NaOET, in this case, O-ethyl. Now I know that when you see this product, you're going to ask a very good question. Okay. That is the intermediate product for this reaction. And I know you're going to ask, well, can't that attack another one of itself? Technically, yes. But the pKa of this is so low. I think the pKa is... I never gave you the pKa of ketone ester. But let me show you what I did give you. Oh, here it is. I gave you the pKa's of a dialdehyde, a diketone, and a diester. So we do have, in this case, an ester and a ketone. So halfway probably in between these two, 9 and 13. We're going to say this is pKa of 11. The thing is, the pKa of alcohol is 15. So equilibrium does favor this side. So technically, with this base, we get 100% of the anion. That doesn't happen if you use NaOET for any of these 3. For instance, this ketone here. Because the pKa is higher, you're not able to deprotonate 100%. But this pKa is much lower, and it's lower than the conjugate acid of the base. So you are going to favor this, and this is going to be 100%. If you have 100% of the enolate, then there's no more of this to attack. So this hopefully calms your fears. You're not going to do a Claisen. You can't do a Claisen with this. You do a Claisen with this, just a plain ester, but not with this dicarbonyl compound. Okay. Hopefully that, again, eases your fears. What is this? I'm not going to draw the mechanism I'm not going to draw the full mechanism, but let me draw at least this mechanism here, this reaction here. Like this, and we kick it out. That's reaction number 2, right, from our sequence. Right there. Oh, that's interesting. So we're able to alkylate. We're able to alkylate which carbon? Alpha, alpha, right? That's the important carbon. So the alpha carbon hits the dot. That dot has 1, 2, 3 carbons after that. 1, 2, 3. The last 2 carbons have a double bond. That's a double bond right there. What is going on with step 3? I think, let's not add heat. I don't want to confuse things. But this is good enough. Sodium hydroxide and water to do saponification. Remember what saponification is? You kick out this O-ethyl and you have an OH here. But since you're under base conditions, you're going to remove that hydrogen. O minus. The rest of the junk, we have this. If you think I'm making a mistake, I am going fast. So what I'm most worried about is copying the right number of carbons. This is still alpha. I'm gonna continue to locate the alpha carbon every time. HCl. Did I use HCl? Yep. HCl. All you gotta do is protonate. The double bond. Here's your alpha. Oh, and I'm going to go even further. I'm going to go beta. Because what do I have here? A beta keto acid. Remember what happens here? With heat, all you do is take your thumb and cover up that carboxyl group and copy. With decarboxylation, you keep the alpha carbon on the main product. So again, what is weird about this is out of this molecule right here at the very beginning, the only atoms I keep are right those atoms right there. That's weird. Okay. Well, to me, it's weird. It seems like it's kind of wasteful. But the fact is, we were able to alkylate at the alpha carbon with very benign chemicals. Sodium methoxide is very cheap. The only thing is you have to add your own alkyl halide. Okay. But sodium hydroxide is cheap. Hydrochloric acid is cheap. Heat, you just put it on the heating mantle, and we get this. So what do we do? Again, it seems like a weird synthesis, right? It seems like a lot of work actually to put something at the alpha carbon, but the reactions are very high efficient. This is called a substituted acetone, because that is acetone right there. Okay, you might, and it's actually fairly easy. You might say, well, aren't there better ways? Aren't there more efficient ways to put an alkyl group on? Maybe we could start with acetone and do that. Acetone is dangerous because if you try to put a negative charge here to make the enolates, you're going to form an aldol reaction. You're not going to be able to keep that anion there to do alkylation. So there are subtleties why we'd want to do all 5 of these reactions to put anything onto that alpha carbon rather than just use acetone, right? Rather than just use acetone. So for practical purposes in the lab, this is a good way to do substituted, there's an E right there, acetone. And that's it. Let me remind you on the exam, and I knew from the beginning I was going to do this. There's not going to be any synthesis. Well, there's not going to be any provide an efficient synthesis. So there's no provide efficient synthesis. But what can I do? I could take this sequence and I could put boxes. So you're not coming up with a synthesis from scratch. You'll have clues along the way. Because for normal semesters, a second. For normal semesters, I could give you this. Make that from this, and then you would have to provide everything. But there won't be any of those. There'll be synthesis still, but either I'll have little boxes, or I'll ask you what do you think the key intermediate is, but not for this exam will I ask you for a full synthesis from the very start. Okay, okay. That is it for Unit 9. Done. Okay, what do I owe? I owe, this is a reminder to myself, I owe practice problems and answers for Unit 9. Those of you who watch the video, it just depends how carefully you listen and take notes. This could be very, very simple. Very, very simple. Or it could be very, very hard. For instance, in this product, let me think of a. Actually, let me look up a problem real quick. While I do that, actually, do this for me. I'm going to give you an ester. Okay, and I want to do a Claisen reaction. This was the last reaction on the last video. So I have to match, right? I have to match the base. And I'll draw it this way. So I am matching that leaving group. The base matches the leaving group. And I think for this one you would have to protonate. You don't have to draw the mechanism, okay? But go ahead and find the Claisen product. I'm going to look up a different problem while you do that. This is just fill in the product. Go ahead and do that. If I'm covering up the screen, let me know. I hope I'm not. I'm just searching my files. Ah, I like that. Okay. Give me one more minute. Let me pick an easier one first. Got it. Got it. Okay. All right, so this is your self check. Also, I'll verbalize what I'm thinking. On the inlay right here. So I'm gonna draw the attacker as is, but I'm gonna flip it. 1, 2, 3. So my attacker is. If you want to know where the alpha carbon is, at right there. If I attack another one of itself, okay, I attack the dot. So here's a dot. Forget that this is an anion. So if I attack that, ultimately I'm going to kick out this leaving group. So I just have to copy that piece right there. Okay, it's the same ester, but no leaving group. All right. Same ester, but no leaving group. When you do this reaction, when you kick out this leaving group, that's a strong base, and you're going to deprotonate this alpha carbon because there's still a hydrogen there. That's why I need acid to replenish it. This is my final product. If you do not get that product, go ahead and do your corrections in red or some other color. I like this product because for a Claisen, you're going to get what's called a beta keto ester because your beta carbon now is there. On the ester side, we go alpha beta, the beta keto ester. So that's problem one. This is not the assignment, so don't worry if you don't catch all of that. Okay? Although this will be relevant to your assignment. Let me show you problem two. And this is a problem that maybe I alluded to in one of the videos, but did not give a lot of practice with. Problem two is going backwards. So I got to draw this as carefully as possible, or else I'm going to screw up. A second. Okay. So my question is, how did I make this? That's the hard part about this enolate chapter, because you have to identify the carbon-carbon bond that was made. So think. We did an aldol reaction at the very beginning, right? And there's the complete reaction, this line right here. Look at your final product. Do you know what bond was made? It was the bond, obviously, between the alpha and the dot. But how do you find the alpha in this case? It's the one with the carbonyl group. So that carbonyl group, the carbon next to it is the alpha. The bond that I made was this one right here. Those are your two pieces. And technically, if you look at only just the right-hand side, you could imagine that, oh, this was an aldehyde. There was a double bond here before it was attacked. But when the attack happened, it became an OH group. Look at that. So my challenge to you is, if you really want to know what bond was made, what do you think was the alpha carbon, and what did that alpha carbon attack? This is your alpha carbon. It attacked that dot. So really, that bond was made. How would you synthesize this? This is a legitimate question, right? Because it's not even a synthesis, it's just a one reagent. So really, here's the question. Here's the question. Fill in the blanks. Okay, so I could ask this question the same way, but the same question, but in a different way. Fill in this, and fill in this. So now, yeah, you're still exercising that part of your brain that says, can I work backwards? Can I figure out how to synthesize this? Technically, for me, it's not a synthesis, it's just fill in the product, fill in the reagent and the starting material. Synthesis for me is multiple reactions. Believe it or not, if you do this analysis, you know that your attacker is that. But the thing that it's attacking, right? The thing that it's attacking is the same molecule. It's off to the side. It's attacking this, right? Imagine the anion right there and attacking this carbonyl group. So how do we make the anion? This is just a plain aldol. You could use sodium hydroxide or sodium methoxide. Okay, something like that. Okay, let me look look up another problem, and then I'll get you your assignment. The other thing is, the way that I keep this straight is, I think this is an aldol product. For any analysis, aldol product. Why is that? I don't necessarily test you whether you can tell me what a beta hydroxyketone is or a beta keto ester is. Okay, but for me and for many students, it helps when you identify this. Isn't this an alpha beta hydroxy? Alpha beta, no, sorry, beta hydroxy ketone. That is the product of an aldol reaction, beta hydroxyketones. And it just happens to be that you're attacking another one of your cells. So you only draw that molecule once. You could have had a crossed aldol, a mixed aldol, where you have two different molecules. I go over that in the video. I'm not going to do that here. What about a Claisen product? Okay. So I gave it away. I'm going to give you a Claisen product. But let me give you maybe a cross Claisen. Let me figure this out real quick. I think I have it. This one right here. So this one's tricky. Okay. This is tricky because we actually have two starting materials. So I should have made this box bigger. But it's still a Claisen. What did we talk about in Claisen? A beta keto ester. For this molecule right here, do you see what bond was made? It was this bond right there. The hard part about this is that we see something, or we don't see something that used to exist. See, wasn't there an alkoxy group off of this dot here? This alkoxy group right here. But it got kicked out. It got kicked out. Okay. Let's do our analysis here. Can you tell which one is the alpha carbon? So on your own, on this molecule here, identify the alpha, identify the dot, and draw a dotted line for this. Go ahead and do that. Alpha, the dot, and the dotted line to indicate which bond was made. The alpha is here. The dot is this one. It's the one that does not have the ester group, the alkoxy group. What that means is that you have two molecules that are reacting. You have the attacker on the left. So all we have to do is draw that molecule and give us a base that will deprotonate that. But we have the attackee on the right. How did the attackee used to look? You know, the attackee, the one that was attacked, was also an ester. It's just that when it was attacked, it lost its alkoxy group. So let's do the easier part first. The easy part is drawing the attacker. And I'll draw it exactly like this, actually. Okay, in this orientation. Already messed up. Okay. It's a little bit, the box again is a little bit small. But let me draw this. See, wasn't that the attacker? It's the left side of the molecule. Before I even draw the other piece, I know which kind of base I'm going to use already. I'm going to have to use an O-methyl group. O-methyl base. I'm matching the base of the leaving group. The base matches the leaving group. But be careful. This is not the leaving group in the reaction. It's the leaving group of this here. But the fact is, if I want to deprotonate this carbon without destroying this ester, I have to use a base that matches that, just in case we get attacked right here, and do transesterification. It doesn't matter if I replace this O-methyl with an O-methyl. It's still an O-methyl. So pretend that your anion is right here. I have to attack a molecule that looks like this. So my other piece is this piece, but we had a leaving group here. You get to pick the leaving group. O-methyl, O-ethyl. But what makes the most sense? I'm combining everything at the same time. So why don't I make it an O-methyl? Because I just thought of this. If this was an O-ethyl, and this base accidentally deprotonates, or not deprotonates, kicks out that O-ethyl, that O-ethyl can replace this O-methyl, and you're going to get a complete mess. That's why I want to match everything, just in case we have these, these substitutions, these replacements. An O-methyl replacing an O-methyl is no big deal. Okay. This is called a cross-Claisen. It's a different kind of cross-Claisen that I showed, because both of them are ester still. What's the beauty of this? I want a hand or a chat. What's the beauty of this molecule right here? What do you notice about that molecule? So either by chat, to me, or to the group, or by raising your hand. What I am avoiding, and I'm going to keep talking until someone answers me. I am avoiding a complete mess. Molecule A and B. Here I have the addition. A attacks B. But where is A attacks A? B attacks B. B attacks A. Where are those combinations? Well, we can avoid some of those combinations because of this group right here. Okay? So I have one person who answered. When I throw all of this into the pool, okay? When I throw all of this into the pool, that base can do anything with any of these molecules. But what do you notice about this molecule here? There's no alpha hydrogens. This cannot be an enolate. And if that cannot be the enolate, that cannot be the attacker. So right away, I have A as the attacker. Now you may ask, well, why can't A attack another one of itself to do a regular Claisen? That was the idea of slow addition, where we have this as excess. So once this deprotonates, most likely it's going to bump into molecule B instead of another molecule A. So think about your product. Think about working backwards. That's going to be your assignment. Okay? I'll write it out. Don't worry about it. But this is the this is the process that I want to see whether you guys can do it or not. Before we get to that assignment, okay? And don't worry, I'll write it all out so everything is clear. Let's go to Moodle. Why did you add another carbon to A? Let me double check that. 1 alpha 1 2 3 alpha 1 2 3. So I think that carbon to alpha. I think I had the right number of carbons. If you're talking about this carbon, when this attacked, I'll even draw that. When alpha attacked to this carbon, this is a leaving group. This is a leaving group. One last check. For the attacker, we have 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6. So I think I'm good with that. All right. If there's still questions about how I drew or why I drew these two molecules, go ahead and let me know. If not, let me go to Moodle and show you what's available. Still need to do that. Let's. One second, let me find it. Okay. All right. Hopefully you can see my Moodle page. There's several office hours this week, but Jose is mainly mainly going to be there in the afternoon or evening. Okay. So the first thing, we're on Wednesday, right? We'll talk about this assignment just a bit, but all videos for Unit 9 are available. I'm gonna put problems. What happened here? I'm gonna put problems right underneath here later today. Unit 10. Unit 10 has 2 videos thus far, so let me get that. Oops. Oh, sorry. Let me get that situated real quick. No. There's 2 videos for Unit 10 right now. I plan to post only one more video for Unit 10. And actually, it's a combination of Unit 10 and Unit 11. So, I'll show you this in just a bit. But I gotta figure this out. This slow. Unit 10 is different than Unit 9. Very different, because we're working with molecules that have nitrogen. Amines. Um, Amines could fit really after a lot of different units. I chose to fit it after the enolate because we're going to form molecules called imines and enamines, and they have very similar, maybe not reactions, but very similar structures to the enolates. We're dealing with stuff at the alpha carbon. All right, so let me pull that up. It's the purple ones. Just put this up where it belongs. All right, so it's right after Unit 10. The point here is that I have one more video to put for Unit 10, and then there's no Unit 11 because I'm going to talk a little bit about Unit 11 and Unit 10, and we're going to skip to the last unit for the exam, Unit 12. So really, when you see the YouTube channel, it's going to be Unit 9, 10, and 12. That will be your exam. Okay, so there's 9, there's 10, and 12 will be coming up probably not till tomorrow, Thursday. Okay, so that will be shown on Moodle when that's all ready. Okay, back to Moodle. Okay, there's one last thing before we get to this assignment that you're going to submit by noon. By noon. And that is, if I could figure this out. Because Jose's office hours are a bit limited, I am going to have a review session on Sunday before your test on Monday. And let me just double check that. Yep. So right now, there's no set office hours on Sunday, either for me or Jose. I think we're asking you to email us. But I want to hold a 1.5 hour review on Sunday, and I want to know who is available and when you're available. Hopefully you can see this. If not, then I totally screwed up. So, can you see the poll? Oh no, not yet. Let me launch it. How about now? So someone messaged me whether you could see the poll. It's asking you a survey. Oh, someone already voted, and I wasn't ready for that. So go ahead and vote. The review session will be 1.5 hours, and I need to know the time. If it's evenly split, it should be anonymous. What is it doing? Are you seeing the results as it's tabulating? Can someone tell me if you're seeing the results? Ah, you're not seeing the results. Only I can see them. Okay, so I have a 5 out of 8 voted. I'm not going to vote. Let me see how many people there are actually. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Oh, there's 8 people. Does anyone else? Oh, that's good too. If you can't meet on Sunday, you don't need to vote. You guys, stink. Okay, I'm gonna end the poll right now. Oh, there we go. It was a 3-3-3 tie a second ago. Okay, how about? Oop, let me share results. How about now? Does everyone see the results? 1, 2, 3, 4, 5, 6, 7. Yes or no? Can you see the results? Okay. This was a ridiculous poll. It's 2-2-3. I'll probably have. Let me just do the 4 o'clock then. Um, if you need help, and you can't meet at 4, you could definitely email me, and I can meet as early as 9:30. All right, so I'll remember this. We'll have a review session at 4. If 3 of you show up, that's great. If it's just me and Jose, um, that's good too. All right. Your assignment is. Let me get rid of that. Your assignment is multiple parts. And the first part is, if you want, go ahead and start a new page. But this is due today, noon. Okay, if you can't see my screen, let me know. One sec. Okay. On Moodle. There's a submission link. Number 1. For this reaction, is an ester. So we're going to do probably a Claisen. I'll give you a base that matches the leaving group. And you do have to coordinate at the end. Your product is this. Let me flip the molecule. And I know that for that alpha carbon, I can definitely make an anion. I'm going to attack another one of itself, but pick out the leaving group. So what really I have left over is this. It's actually the same. This was unintentional. It's actually the same action here, except that instead of a propyl group, I have an alpha group. No big deal. Compared to two products, again, they're almost identical. Oh, forget. Oh, there it is. There. They're almost identical. What do you think my question is going to be? For this reaction, you don't know what my question is going to be. describe in your own words the mechanism. If you want to draw out the mechanism first and then describe, that's perfectly fine. But I'm looking for types, not type, I'm looking for text. Either handwritten or typed. Here are the stipulations. Each step. Because I want to, for me, there's a lot of internal talk when I take an exam. And I'm wondering if other people learn that way. Do they talk themselves through a problem? So for each step, use 4 to 10 words. Maybe you could do it even in 3. So if there's a deprotonation, that's only 1 word. So say something like deprotonate the alpha carbon. That's between 3 and 10. I'm only looking for a phrase or a sentence for each step. So if I see like 8 lines of writing, you're telling me that there were 8 steps. Okay? So 1 line per step. 1 line per step. Does that make sense? I want to use your own words. You can go back to the video and see how I described it, but I think which is great, but then if you put it into your own words, you'll be able to recall a lot faster on the exam. So this is going to help with mechanisms. But not only will this help with mechanisms, right? When you describe the attack, you can describe what you're attacking, you describe what the attackee is. After doing that, it's going to help you with retrosynthetic analysis, breaking stuff down. Because this is the second problem that's due at 12. The second problem is this. What starting material? How am I spelling? Okay, plural or not plural? I'm not sure yet. What starting materials and reagents, plural or not plural, were used to make. So for the first problem, it's based off of a Claisen. The second problem is also based off of a Claisen. All right? It's going to be asking you to do this type of analysis. Well, this type of analysis, but this was for an aldol. Okay? Oh, where did it go? This type of analysis. Okay. I'll give you a clue that it is going to be crossed. You could have 2 molecules. What starting materials and reagents were used to make this molecule here? It's a little bit tricky because it's oriented in a slightly different way. Okay. So I've given you a lot of clues. One clue is that it is cross, so you're going to have an A and a B. The other clue is do this analysis. Do this analysis, but for this target right here. Okay. So in one screen, you could handwrite this if you want. If you want to type this out, you can, but then you're gonna have to draw and stick a picture of your starting material and reagents. Okay. Basically, I want this. I'm just redrawing this. If you could do this problem and it's accurate, then you're cruising for Unit 9. You're doing very well. Okay. Try your best. Let me give you a couple announcements right now. I'll come back to this page, don't worry. Okay, Jose has no office hours today. I think he's stuck at Emory on the campus for the whole day. Seriously? I have one at 1 o'clock. So do this assignment, and if you want to hop on and talk to me, I'll be there from 1 to 2. These are the rest of the office hours I added. I'm actually going to do a review session at 4 on Thursday as well, just like a mid-week review. Okay, and we could do stuff like that. I mean, we could do stuff like this if you're worried about the type of problems that you might get. Um, we'll do. I'll make up reaction. I'll make up problems like this. Okay, working backwards. Okay, so that is on Thursday at 4 o'clock. All this jumping back and forth. Okay. Is there anything else? I owe you practice problems. I'll put up another video for Unit 10, which is going to be a total of 3 videos. The lab. For me, today is a big work day. After office hours, I'll just be concentrating on the class. I am going to most likely put something up for lab today, which will be lab number 4, and I am going to still hold to the due dates. It will be about 48 hours after I post. So there will be something due maybe Friday for your lab. Don't forget that I think lab 3 is due today, I think. And refer back to lab 2 to help you with lab 3 to see what I'm looking for in terms of the stoichiometry table. You don't have to draw a procedure, I don't think. So let me just remind myself about lab 3. Oh, here it is. So lab 3 is due 5 o'clock today. 5 o'clock today. All right. Let me go back to the document camera. Are there any questions or problems? Let me go to the chat. If you want to raise your hand or put anything in chat, you could do that. If not, again, I don't know if you can see the whole thing, but that is what's due at 12 o'clock today. Okay, so you have about 50 minutes. All right. All right. So if you want to get started on this and we're all good and you have no more questions, you could go ahead and log off Zoom. And at 12 o'clock, I will collect the assignments from Moodle, whoever handed anything for these 2 problems. All right. All right. I'm alone. Oops. I'm recording.